There's probably a point in time in high school or early college when you're handed a periodic table with a list of trends on it. For the astute among you, you probably put together that the periodic table's strength doesn't come as a memorization tool, but as a tool that organizes the elements by their common characteristics. But the problem with grouping these things together and throwing them all at you at once is that there's a lot of big words here that mean absolutely nothing to you yet in your chemistry journey. So most people just memorize the trends, being up and to the right, being down and to the left, and hope to never see these concepts again. But hidden within this forest of syllables is one of the most important concepts in chemistry: electronegativity. The textbook definition of electronegativity is the tendency for an atom of a given chemical element to attract shared electrons when forming a chemical bond. But I find that definitions like these can actually hurt as much as they help. So instead, let's do an illustration. Okay, let's start with an oxygen atom, and let's bind it to a different atom. Carbon's a good choice. When we show chemical bonds, we typically draw a line between the atoms, but this isn't really an illustrative way of showing what's going on. In reality, this line represents that these two atoms are sharing electrons, one given by each atom. This kind of bond is called a covalent bond. Co meaning together, like copilot or coexist, with valent referring to the electrons on the outside of the atom, or its valence electrons. However, even this illustration falls short. It turns out that bonds are rarely truly covalent, meaning shared evenly. Atoms can be a bit greedy, and it turns out that these electrons spend more time closer to the oxygen than the carbon. I like to think of it as a kind of atomic popularity. The oxygen, being more popular than the carbon, tends to get a little bit more attention from the electrons. And since the electrons are negatively charged, it makes this entire oxygen become slightly more negative. We show this partial negative charge with this lowercase delta, but that's something I'm going to talk about more in the next video. So now we can put the whole term together. The electro part of electronegativity refers to the electrons being pulled closer to one atom than the other, where negativity is a natural outcome of that, where now that atom becomes more negative because of the added electron density. So why does this happen? Is it just some magical property of oxygen that it pulls those electrons closer, or is there some concrete reason why? To answer that question, we have to jump back into our trusty periodic table. Here we can see that oxygen and carbon are on the same row, meaning they have the same number of electron shells, or layers of electrons. But since oxygen is 2 columns over, it means that it has 2 more protons, or positive charges in its nucleus. So here's what that looks like in a really simplified view. They each have 2 electron shells, but oxygen's 2 extra protons mean that it has a stronger pull on those electrons, and it can actually pull those shells closer to itself, meaning it both has a smaller atomic size, which is measured by the distance of these electrons, and when you put it in a bond with carbon, it has a greater pull on the shared electrons, making it more electronegative. We can make this difference even bigger by going the other direction on the periodic table. By going down a row from carbon to, say, silicon, we add another shell to the atom, and despite the added protons, this extra shell is now so much further from the nucleus that it has a much harder time pulling in those outside or valence electrons. This means that any atom found on the same row, meaning that it has the same number of electron shells as another atom, but is further to the right, meaning that it has more protons, has a stronger pull on the electrons in a bond. And any atom found on the same column as another, but higher up, means that it has less electron shells, which means electrons are closer to the nucleus, and it has a stronger effect on those electrons. Now these two factors, when combined, give us the textbook trend of electronegativity, that the further up and to the right on the periodic table you go, the more electronegative an atom becomes. Now this video just talked about electronegativity and why it happened. In my next video, I plan on talking about polarity, which is a natural outcome of electronegativity and one of the many reasons why it's extremely important.